The main concept of the simplex method is, one, start with a basic feasible solution. One, start with a basic feasible solution. Two, from that basic feasible solution, go to an adjacent basic feasible solution. The condition for going to an adjacent is if the adjacent provides a better z-value. If it doesn't provide a better z-value, we claim that point to be optimal. That's it. Three, to make sure that as we go to the next adjacent feasible solution, to make sure that the next extreme point, the next adjacent extreme point that we are going is feasible, we use a technique called min ratio. We will find the ratio and we will pick the least among that ratio. Least among that ratios is called min ratio. There is no least min ratio. Least min ratio means nothing. There are ratios, and least among that ratios is named min ratio. The column that we have at the end of the tableau is not the column of the min ratio. It's the column of ratio, but we would like to find the min ratio. That's why when we have that numbers, we will mark by one of them and we say this is the min ratio. Okay? So the three important things that we needed to do are pretty straightforward. What I do today is a continuation of the same thing. Is a continuation of the same thing. What we said was that you need to start. Simplex method starts with what? A basic feasible solution. Okay? And then we came back to this notion. How do I find a basic feasible solution? Is it by trial and error? Do I go to somebody else? Do I send a call help desk? How do I find a basic feasible solution? We introduced one of those techniques to you. And what was that? If the origin is part of the feasible region, if the origin is part of the feasible region, then you have the origin as your basic feasible solution. And when we say part of the feasible region, doesn't mean in the middle of the feasible region. A corner point of the feasible region. In that case, your first basic feasible solution is very easily done. You just use the standard form, put them into the Tableau with S1, S2, S3, S4, as many of them as you have, as your basic variables. So if that is the case, then that is your basic feasible solution. From that point on, everything is the same. Tableau, 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 until you reach optimal solution. However, if that point is not part of the feasible region, then you don't have any easy way of starting with a basic feasible solution. Today's lecture, today's topic is about that case. It relies on the fact that you know how regular Tableau format works. So if you don't know how it works, this is like some extended language that I will be talking to you. If you know how it works, this is just a continuation of that. The only thing that we are doing right now is considering a different case and how to approach that. So let's talk about this. Does anybody need to do homework for other classes? We can give you 10 minutes to finish your homework if you have to. Nobody. Okay. So, does anybody need to finish a homework for this class? We can give you an hour. I can stand here for the next hour until you finish your homework. Okay. Other than that, please pay attention. For those of you who will be sitting in the traditional exam this coming Saturday, this coming Monday. Yeah, I still am Saturday and Monday mixed up. I use the Mayan calendar, so in Mayan calendar Saturdays and Sundays are the same on Mondays. Okay. Anyway, for those of you who are coming on Mondays, for the Mondays traditional group test, remember what you are dealing with is not just the simple two topics that you will have under topics 4 and 5. Everything from the website to your textbook up to that may be asked also. So you need to know the stuff. I specifically will ask questions about the website because as of now, which is something like 7 weeks through the class, I still see people that when I say this thing is on the web, they say, a website? Oh, I need to check that. And you know who you are. Okay? So, let's start with this. This is an example. This is an example similar to what we did in our practice. These were the corner points. These were the corner points. So for this problem, the solution was very simple. Because origin is an extreme point of the problem. What this problem has, when I write the LP, has one big characteristic that I can easily see. And that characteristic is that all the constraints are in the form of less than or equal 0. They are all in the form of less than or equal 0. Because in the form of less than or equal 0, all the slacks that I am going to put into those constraints to make them in a standard form are in the form of plus s's. So it is plus s1, plus s2, plus s3, which makes s1, s2, s3, and whatever it is, a good candidate to go into the basis. And what is a basis? It's the set of basic variables. Okay? By the way, we have incentives for the people who speak, as you know. Okay. So in this case, it was straightforward. However, let's add another constraint to this. And we're going to add a constraint like that to the problem. What it does, it immediately takes this point, which was the origin, off the list of the feasible extreme points. Of the list of the feasible extreme points. If that is off the list of the feasible extreme points, then I cannot use S1, S2, S3, S4, S5 as my basic variables. Because if they are basic variables, it means that x1 and x2 are 0. x1 and x2, 0 refers to this point. And this point is not a feasible extreme point. Simplex method requires, number one, to start with a feasible extreme point. So if you cannot start with a feasible extreme point, whatever you do is meaningless in Simplex method. So you are either on the mercy of trial and error to say, how do I find one of these? Of course, if it is a two-dimension, something like this, you can actually calculate one of those and say, oh, this is the feasible extreme point. So you would calculate what the actual basic variables are here and what are the non-basic variables. And then you go through one of those processes that we went, like topic 3 or 4 or those things, 3, and then you will find what the Tableau should look like. But that's not what we are going to be doing. We are going to be using a different technique. And to use this technique, we need to go back and talk about the reason that we choose a variable. Okay. Max z equal 10x1 plus 9x2 minus 4x3 plus 5x4. In a standard form, that line reads z minus 10x1 minus 9x2 plus 4x3 minus 5x4 equals 0. There is no equal sign here. There is no max here. It is like a regular equation. We go back to our common sense approach. We said, first of all, I have started at 0, 0, 0, 0. 0, 0, 0, 0. Z, 0. S1, S2, S3, S4 equal my basic variables. X1, X2, X3, and X4 are my non-basic variable. And I say, is Z0 optimal? I will look in here. And so all these things are 0. I can do better than 0 by raising one of these values. By raising them from what? From 0. Increasing them. And as I increase those values, Z increases. For example, I can pick X2 and I say, oh, I'm going to increase X2 instead of 0.1, 0.2, 0.3, 0.4, 0.5. And as I increase X2, Z becomes 9 times 0.1, 9 times 0.2, 9 times 0.3, and so on. It keeps increasing. It keeps increasing. I can do the same thing for X1. One at a time. One at a time. I'm just making a case. Why one at a time? Who can tell me? It has 5 effort points.
Go from one point to another
Okay.
You're trying to go to the next extreme feasible region. The adjacent is the optimal point.
The adjacent is the key point. You're trying to go to an adjacent extreme point. And an adjacent extreme point and an adjacent extreme point is an extreme point that is different with the previous one only in one variable. That's what we're talking about, one variable at a time. So I can increase one variable to what I want. Increase, whatever it is. Okay, back to common sense. Warren, back to common sense. Okay, these are like money. If I have to choose one of these, which one would you go with? You're not Warren. You're not Warren either. This guy is Warren. Which one of these would you select? You would select X1. Why? It gets you the greatest yield. 10 times that. Okay? 10 times that. Now, in terms of a standard form, which is in the Tableau, this is not in the Tableau. Standard form is in the Tableau. What would you select?
The greatest negative.
The greatest negative. Is the word greatest negative correct? It's the most negative. Greatest negative in here is 5. That's larger than all the other negatives. It's the most negative, which makes this minus 10. Okay? It's just the words. The careful with using the words. So this is how you go. That is what the rule comes from this. And it says, how do you select the entering variable? How do you select the entering variable? You go with the most negative in the zero. That's common sense. We can call that Warren's rule instead of simplex method. Okay? That's what this is. Now, it would be good if we could increase it as much as we want, but we cannot do that. What would stop us? You cannot increase this as much as you like. Why? Because there are constraints which would stop you. There are a set of constraints. And if you keep increasing this, at some point in time, you will hit a wall. To find out which one of those constraints would stop you first, what would you use? Mean ratio. Okay? One of your good friends. Mean ratio would stop you. In this case, one of the problems that we have is that we cannot find a feasible extreme point easily. We come back in here. We said, we will select x1 because it has the most negative. In terms of this, this is the most positive. Well, we talk about this. I'm not choosing this, although this is good also. I'm not choosing this, although this is good also. It will give me reward because I have to choose one of them at a time. So I go with the most reward as I think. I'm not approaching this, which in this case is positive. Why won't I approach this? Because if I increase x3, my z from 0 becomes even worse. I increase x3 by 5 units, my z becomes minus 20. From 0 it goes to minus 20. I'm not approaching that because the coefficient is negative. Which means common sense, Warren's rule, common sense, I'm not approaching something which is negative. In here, I'm not approaching something which is positive. So if all these things are positive, what would I say? That's the optimal solution. That's the rule. If everything in the 0 is positive, it means in this original form they are negative, and if I increase them, I would make the z worse. Okay? One of the things that we want to talk about it in a second is this. If I have a Tableau at some iteration, not the first one, at some iteration, and again, as you remember, this is not a legitimate Tableau, so x1 and x5, okay, x1, x2, x3, x4, x5, s1, s2, okay, 0, 0, 0, 1, 0, x2, negative 3, 1/2, 4, x3 negative 1, 0, 2, x4, 3, 2 and 1/4, x5, 0, 0, 1, s1, 2 minus 1 and 3, s2, 5, 1/2 and 1/2, and z value 10, 4 and 6. It's not a legitimate Tableau. I just made it up. If I have this, don't forget, each one of them represents an equation. Just like the first one. How did we do the first one? We took the standard form, copied them into the Tableau. What about this one? It's after some row operations. I ended up with this. I'm looking at the numbers and they are okay to me. x1 is a basic variable, so it is 0, 1, 0. x5 is a basic variable, so it is 0, 0, 1. Right hand side is positive. Right hand side is positive. And this looks like a legitimate Tableau. Okay? Just on the surface it looks like a legitimate Tableau. But don't forget, every one of them represents an equation. What is the equation for the first one? How do you write that equation for the first one? It is 1x1, 1 plus 1/2 x2 plus 2x4 minus s1 plus 1/2 s2 equals 4. That's how you put them from the standard form into the Tableau. And the second one would look 4x2 plus 2x3 plus 2x3 plus 1/4 x4 plus x5 plus 3s1 plus 1/2 s2 equals 6. Yes.
If you're doing the equation on the line, I see that you have 2 slacks.
Mm-hmm.
I'm having a problem with that.
He's having a problem because there are 2 slacks in one equation. The first one only had 1 slack in each equation. Now this one has more than 1 slack in each equation. What is the problem?
If the slack is 0, that just means you're on the line. So you're not going to see the value in the equation because it's 0 times the slack. But
Okay.
if you're not on a certain line, then you'll have your value for the slack, so you're going to see it.
The point is not just the slack. The point is basic variable. How many basic variable? Oh, let me write the z also for you. And the z is going to be no x1, negative 3x2, negative 1x3 plus 4x4, 3, sorry. No x5 plus 2s1 plus s2 equals 10. What did you say? Just kidding. It was 5 in here. We'll go with 5 in here. The question is not whether there is one S1 here in each equation or two S1 or both S1 and S2. The question is about the basic variable. What is your basic variable? In this case, the basic variable is x1 and x5. The question is, in this set, is there more than x1, 1x1 in any of these equations? There's only one x1 here. There's no x1 here, no x1. 0, 1, 0. What about x5? No x5 here, no x5 here, 1 x5 here. It has 0, 0, 1. So it doesn't make any difference. And why it doesn't make any difference? Because it is processed. We have done the row operation. We have added a row to another row. We have multiplied a row by a number added to another row. So it is going to change as you go through this process. But this is what it is representing. This is what the Tableau is. And that is our representation. Any question about this? It's very important that you know what these things are. We are going to connect now this with this with this all together to help us find a way to do something. Okay? About the cases where this specific point is not a basic feasible solution, like this case. And how is that I'm going to do that? I'm going to introduce a new variable. And I'm going to call that variable an artificial variable. Okay. We're going to have introduce a variable called artificial variable. We will, for a couple of minutes, we will stop this discussion. We go back to something in here. This is a feasible region for a problem which has x1 greater than 0, x2 greater than 0, and probably x plus y less than or equal 5. Less than or equal 5. If I add to this problem an equation, a line itself. Like for example, the line of x2 minus x1 equals 0. This is that line. This is the line of x2 minus x1 equals 0. So my set of constraints are something less than or equal, something greater than or equal, something greater than or equal, and something which is equal to 0. Where is the feasible region of this problem now? Where is the feasible region of this new problem? The feasible region of this problem is now only this. That is the feasible region of this problem. It is only that piece of the line. That piece of the line is on the line, and that piece of the line satisfies the other constraints. So every time that you have an equality, somehow you're dealing with a strange situation. You may draw all these things, but if there is an equality in there, it means it's on that line. If it is more than 2 variables, it's on that plane. If it is more than 3 variables, it's on the hyperplane. But it is on that one, the one that has equal sign in there. Now, when we have less than or equal sign, we can add slack variables. When we have greater than or equal sign, we would subtract those variables. If we have equal, what do? Nothing. It is already equal. So it is, when you have equal sign, we do not add any slack variable. We do not subtract anything because it's already equal. We do that to make inequalities equal. But if it is equal itself, we don't do anything. Okay? So, back to this. I will be using an artificial variable. An artificial variable will be used where I do not have a basic variable identified easily. An artificial variable will be added to that. An artificial variable will be added to the standard problem, to the standard form of the problem, not to the original problem, to the standard form of the problem. We call artificial variables R1, R2, R3, whatever it is, and we will make sure that they are greater than or equal to 0. But there is one problem. There is one problem. What is the signs in a standard form?
Equal sign.
She says equal signs. And the rest of you will say, not necessarily.
Are you talking about from
the main constraints. She says standard form are all equal sign, and the rest of you will say true. Okay? And then you say, if that is the case, if it is balanced, and you're adding an artificial variable to one side of it, what would happen? You make it unbalanced. You make it unbalanced. So you cannot have the equal sign anymore. You add an artificial variable, you add an artificial variable, you will make it unbalanced. So what would you do now? I say, okay, I come back to common sense. And I say, I'm going to pretend like nothing happened. I add artificial variable, I'm not going to change the sign. I say, you can't do that. I said, hold on. God's not done with me, hold on. Okay? I'm going to just pretend that it is not there. But you say, oh, you're saying that it should be greater than or equal to 0. How can you pretend it is not there? I said, yes, I'm just pretending. It's a pretend game. Kindergarten. Remember, pretend. We are pretending it is not there. But at the same time, I'm going to do something to make sure that it will not be there down the road. And then you say, really? How? I said, you remember this discussion that we had? Why didn't we want to approach X3 at all? Because it has a negative coefficient in here. Okay? That's what I didn't want to approach it. And say, okay, let me use that concept. And I say, I will add artificial variable, but I will also add artificial variable in here, what makes its coefficient a very large number with a negative sign. A very large number with a negative sign. So I will use a very large number, and I say, what is a very large number? You say 2,000, 5,000, 10 billion, zillion, dillion, whatever it is. And you say, oh, there's too much difference between the opinions. I'm going to just use something called M. Okay? That just not because it is my first initial, but that's because the textbook says. So I will use that. That is representing a very, very large number. You say, what do you mean? What is it? So I'm not going to use a specific number. It's a very, very large number. You say it's 1,000, I said larger. You say 10 billion, larger. Whatever it is. It's a very, very large number. But I don't want to get involved with the actual digits and all those things. I just say it's a very large number, and it is positive. So I'm going to add an artificial variable, but at the same time, I'm going to subtract it here. Minus MR1, minus MR2, minus MR3, whatever I have, minus MR4. So when they come back here, they become plus MR1, plus MR2, plus MR3 equals 0.
Every time you have
Every artificial variable that you add, you do minus M. Now, is it true for minimization and maximization? No. But we are talking about maximization problem. Okay. In maximization problem, you do minus MR. And then you say, so what, Dr. Salimi? You did that. You went through this and you created that and so and so and so. What does that mean? I say now, R1, look at R1. R1 is only in one constraint. It's not in the other constraints, so it is in the form of, I don't know, 0, 0, 1, 0, 0. Looks like a very good candidate for basic variable. So let's start doing an example. Maximize, we'll use the same thing. Z equals 10x1 plus 9x2 minus 4x3 plus 5x4. Maximize this. Subject to 3x1 plus x2 plus 2x3 plus 3x4 less than or equal 20. Negative x1 plus 2x2 plus x3 minus x4 equals 10. Two x1 plus 3x2 plus 2x3 plus 4x4 greater than or equal to 15. x1, x2, x3, x4 greater than or equal to 0. Now you go ahead and before I write them, you go ahead write the standard form of this problem. I will just erase the stuff and rewrite those, but you go ahead and write the standard form of the problem. It is, of course, a legitimate question to ask, what is the standard form? But I'm assuming that you all know the answer. And then you say, okay, I have to do the same thing about that. So I'm going to do this, that. That's the standard form of the problem. And then you say, okay, I have everything ready. I can do my Tableau. You shaking your head? Do I have everything ready? I can start my Tableau. So you cannot start this on a Tableau directly, can we?
No.
Okay. Why not? Because you're looking for the candidates for basic variables. What is a good candidate for a basic variable?
There's only one occurrence in the next.
There's only one occurrence of that variable anywhere in here. Anywhere in here, there's one occurrence of that variable with a coefficient of +1, and it is nowhere else. So is Z a good one? Is S1 a good one? Okay. So for that and this, I don't have a problem. Is there anything in this one that's a good candidate? They say X3 is a good one. Okay, those of you who have been cured for your neck, please shake your neck such that I can actually see a couple of them. 1, 2, 3, 4, 5. I didn't say do this. So 5 people. Son, well, you shake it? You shook it? Okay, well, let's. Okay. X3 is not a good candidate because true, it's here with a coefficient of 1, but it exists other places. Can I make X3 a basic variable? Yes. You can make X3 a basic variable, but you have to do something. You have to do row operation to get rid of X3 in here. You have to do row operation to get rid of X3 there. You have to do row operation to get rid of X3 there. If you do that, X3 becomes a good candidate for a basic variable, but that's a long shot. Okay? Why is it a long shot? Because I don't know after I do that any one of these things would end up to be positive or not. If they become negative, then X3 is not a good candidate. So it's a trial and error. We are not going to do that. So X3 is not. So this one really doesn't have anything that I can rely on. What about the next one? A says we do have a candidate. Okay? It says we do have a candidate. Do we have a candidate? Looks like this guy is a candidate, but it is one of those things that is not going to work because it has a negative coefficient. And of course, all the students at those 2 universities know how to get this positive. What do they do? What do they do? Those are students. They multiply this by a negative sign and they say, this is a candidate. But you at Morgan State University know that this is not a good approach. Why? It makes this negative. And if the student in that so-called university says, so what is your answer?
You're wrong. There wouldn't be a
You cannot apply simplex method. Why not? Simplex method requires positive right-hand side value. Okay, so this is where you remember that on such a lovely Wednesday you were sitting in a classroom full of bright minds and a teacher that was talking about something called artificial variable. But as this one is taken off this list, you have also erased it from your memory. So we'll do that again. I say, no problem here, so I'm going to add an artificial variable here. And then you say, Dr. Salimio, if you add it with a red, we get confused, so we will add it with blue. And then this one is problematic, so I'm going to add another one here. And then you immediately remember that this evil twin of mine will not tolerate if you do not add that in here. And then you say, whoa, you added something in here. Okay, you have to subtract it from the 0. Okay? And then I say, okay. So I do an MR1 and MR2. And then you say, Dr. Salimian, hold on. You are not in that university. You are here. Don't fool us. You just said subtract. This is a standard form. In original, I actually subtracted. I said minus MR1, minus MR2. Then I brought it to the other side. They became positive. Okay? So, that looks fine. No problem so far. Why not? Because S1 is 0, 0, 1 S1, no S1. R1, 0, 1, 0, no R1. 0, 1, 0, no R1. That's an MR1. You say, can't get rid of that. MR1, there's an MR1 in there. I say, okay, we need to do something about that. What about R2? 1, 0, 0, good candidate. There's an R2 in here. So we will get rid of this. How do I get rid of MR1 in there? How do I get rid of MR1 in there? I will look in here to see where R1 is. I'm going to multiply that by minus M and add it here. Would that help me get rid of MR1 up there? Yes. What about MR2? Same thing. Multiply this, where R2 is, by M, by minus M, and add it up there. See if you can help me do that. Multiply and add. See what we get. Either do it in one step or two steps together, as you do. See what the new Z will be. These things would remain the same. Only that one will change. Now you are young minds, fast fingers, old, computerized, digitized. You're the new age. And you are telling me that it is Z. You're looking at me or you're doing? So now with that Z and this, can I use R1, R2, and S1 as my basic variables? Yes, because there is one S1 in this one, no S1 anywhere else. There is one R1 here, plus one R1 here, nothing in here, and nothing in here. There is one R2 here, nothing here, and nothing here. So now I can start my Tableau. So Z, my basic variables, which are S1, R1, R2. The problem under X1, I have 3 minus 1 and 2, 3 minus 1 and 2. Under X2, I would have 1, 2, and 3. 1, 2, and 3. Under X3, I would have 2, 1, and 2. 2, 1, and 2. Under X4, I would have 3, negative 1, and 4. 3, negative 1, and 4. Under S1, I have 1, 0, 0. Under S2, I have 0, 0, negative 1. Under R1, I have 0, 1, 0, and under R2 I would have 0, 0, 1. On the right hand side I have 20, 10, and 15. The 0 comes from here. Under x1 I have minus 10 minus m. Under x2 I have minus 9 minus 5m. Under x3 I have 4 minus 3m. Under x4 I have negative 5 minus 3m. Under S1 I have 0, under S2 0, under R1 0, under R2 0, and minus 25m. Which one did I make mistake?
No, you didn't.
S2? There's no S2 here. S2 in, I'm sorry, where? This? It shouldn't be 0? What should it be? You see that? I multiplied this by minus m, but I didn't add it here. That is plus ms2. And that's what he kept telling me, and I didn't pay attention to. So there is a little m here under S2. There is a little plus m. So this is the Tableau that we will start our first iteration with. Same things that we wrote underneath the other Tableau. What is the first thing that we write? Solution. We say the solution. For you that you have room, please write these things underneath the Tableau. Okay? Write these things underneath the Tableau. Solution. What is the solution? x1 equal x2 equal x3 equal x4 equal 0. That represents the origin. S1 equal 20, S2 equals 0, R1 equals 10, R2 equals 15. What was the second step? What is the second information that you need to write underneath the Tableau?
This is not the optimal solution.
Is this an optimal solution? Is this an optimal solution? That is what you usually do. Okay? In this case, we will add a little bit to it and we will modify that line. In this case, we would ask, whether this solution is feasible or not before we say optimal. No infeasible solution ever is optimal. For the infeasible solution, you never ask that question. It does not make sense to ask whether something is optimal or not if it is not feasible. In the previous cases, we started with a feasible solution. We continued with a feasible solution. In this case, this solution is not feasible. So that sentence is changed to this. Feasible no. Okay? Feasible no. It is not feasible. The reason. You need to say the reason. Artificial variables in basis and very, very important, and greater than 0. So artificial variables can be in the basis and be 0. That we can have. But artificial variables in the basis and greater than 0. Where is the basis? Right where? It's right here. This is the basis. Basis is the set of basic variables. Okay? So it is in here. R1, R2 in the basis, and their values is greater than 0. So this solution is not feasible. If a solution is not feasible, we don't even ask about optimality. But we will continue with the rest of the step. What is the next step? What is the next thing that we said? What is the third thing that we say? We say entering variable. How did we select an entering variable in a maximization problem? We looked for the most negative. We look for the most negative in the 0. Okay? What is the most negative number in here? For x2, which is minus 9 minus 5m. That is the most negative. That's the most negative number. This one, 4 minus 3m, minus 5 minus 3m, minus 10 minus m are all larger than this. This is more negative. Okay? So this is my entering variable. Whew. Where are we going? I'm getting... This is my entering variable. See how easy you can make mistakes?
Circle wrong stuff.
If you don't write them underneath each other, that's what is going to happen. That's my entering variable. Okay, entering variable x2. The reason? Most negative in 0. Next one, leaving variable. Leaving variable. To do the leaving variable, we will do the ratios and we will pick the min ratio.
We have to arbitrary.
Yes, sir.
So, will you be picking arbitrarily between R1 and R2? Yeah.
Haven't gone there yet. Okay. So the ratios are 20 over 1, 20 over 1, which is 20, 10 over 2, 10 over 2, which is 5, and 15 over 3, which is 5. And we will select among these two. If you were, which one would you select?
R1.
He's selecting R1. Why?
That's the row with most zeros.
That's the row with? What is that?
The most zeros.
The most zeros. Okay. That's one thing. What else?
2 is easier to work with than 3, I guess.
It's easier to work with 2 because you're multiplying by 1/2, then 3, which is 1/3. Other than that, it's just a process that you have to go through. So we will select that. Okay. Now in the long run, that may not be a good selection, but we don't have any other way of doing it. Okay. So we'll pick one arbitrarily. Now if this was 17, I would definitely go with that. I don't want to deal with 1 over 17 numbers, at least not that early. Okay, so this is going to be, now true or false? I'm not doing this calculation, minus 25m over minus 9 minus 5m for the min ratio, because this number is negative. No, because this number is negative.
That has nothing to do with it.
Yes, no,
That's false.
no, has nothing to do with this. We never do this. Now this is a wrong Tableau because this number is negative. M is positive, minus 25m is negative number. We cannot have negative number on the right hand side. That's true or false?
You can have a negative.
You can have anything in here. Okay? Now I ask you a test question. Why can't you have anything in here? Look at what I have erased somewhere down there. It says, finish the class? We'll finish the class?
Yeah, 7 minutes.
6.
I have 6 minutes, or I have 6 minutes past the time?
6 minutes left.
6 minutes left. Oh, thank you, bro. Okay. Remember those things that I had, non-negativity constraints? I said x1 greater than 0, x2, x3, x4, s1, s2, R1, R2. Did I say anything about Z? Z is unrestricted. It can be anything. It can be anything. So, that, you process it, you go to the next Tableau. You process it, you go to the next Tableau.
For the explanation on the leading, do you just put, you pick arbitrarily?
You say leaving variable R1, reason, mean ratio, and in parentheses you put arbitrary, which means there is a tie. And then you say my pivot is 2. And then do you do an iteration, which means you create a new Tableau. How do you create the new Tableau? You will have one thing in mind. One thing, this picture is going to be in your mind. This picture is going to be in your mind. In the next Tableau, what is replacing what? X2 is going to replace R1. This is the picture in your mind. What is R1 column right now? This picture in the next Tableau will be under X2. That is your goal. How do you reach that goal? Through row operation. If I want to look like this, that number needs to become 1. To make that 1, multiply by 1/2. In the next Tableau, you use this Tableau to go to the next Tableau. Now some fun. Okay. Oh, by the way, this is the topic 6 done. Okay. So next time after the test we will start topic 7. This is topic 6. And then you say, oh no, you haven't solved this. I said, you can do it. Because you did it in topic 5. The rest is regular simplex. You continue. Okay? 3 important things. Okay? And we will give effort points to whoever gives some answer that is really blowing the mind. Okay. Minus m minus 5m plus 10,000 minus 0.00000m 1. Minus 10 billion plus 0.00000000001 m. Okay. Which one of these numbers is the most negative number? Raise your hand. Oh, you said you didn't know how many zeros it has. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros and then 1. Raise your hand. Okay, we'll vote. That's the first one, that's the second one, that's the third one, that's the fourth one. How many people say the first one is How many people say the first one is the most negative? Raise your hand. Nobody. How many people say the second one is the most negative? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 18, 19, 20. Are you going with the trend or what? Okay. How many people are telling me that the third one is the most negative? Nobody? How many people are telling me that the fourth one is the most negative? 1. Okay. 2. Anybody else wants to join the 3? Anybody else? Okay. We are going to now make this a little bit lopsided for these 3 people. Apparently nobody likes those 2. So we're going to change that. Number 4 is that number. Okay? Number 4 is that number. We are going to change that to minus 4.99999 m, and we're going to make that minus 10 to 25. Between that and this, how many of you guys from here wants to jump here? Any more person with that other than the 3? We are going to change that, and we are going to be adding 10 to 99. 10 to 99 means 10 and 99 zeros in front of it. How many of you want to jump from here to here? None? Are you telling me this number is more negative than this number? So how many of you would want to jump from this to this? None? I mean, you said that, I don't. The decision to find what is the most negative lies with the coefficient of m. If they are equal, then the other thing becomes important. If they are not equal, it relies with the m. Have a good time. I'll see you during the test. Some of you.